Well, we can go ahead and get started. Thanks so much, everyone, for coming to the LPI virtual seminar this week. And this week, our guest is Dr. Joe O'Rourke. Dr. O'Rourke is an assistant professor at Arizona State University in the School of Earth and Space Exploration. And today he's going to be talking about the Venusian heat engine and whether it's running quickly or slowly. Fun fact about Dr. O'Rourke that he gave me ahead of time is that he was just 10 days old when the last NASA mission reached Venus. So this is little fun fact, but hopefully with the selection of the 2 missions to Venus now, that'll the next generation of scientists won't have to wait quite so long. But just as a reminder, please leave your cameras off and microphones muted during the talk. If you have any questions, please feel free to go ahead and type them into the chat box, and we'll ask them at the end of the talk in the last 15 minutes or so. With that, thanks so much for coming, and take it away, Joe.
All right. Thank you, Sean, for that introduction, and thank you all for having me. It's great to see those of you who I know in the participants list, and it's nice to meet those of you who I don't know. Someone says they can't hear me. Is anyone else having that problem?
I can hear you fine.
Okay, great. Well, I'll keep talking. And so the fact that I was able to see that chat should clue you in to the fact that I am monitoring the chat. So if you have questions along the way, no promises, but feel free to type them in the chat and I'll try to address them in the moment if they seem like something I can quickly answer. Okay, so I was asked to speak about, and I'm very excited to speak about, the general question of whether or not the Venusian heat engine is running quickly or slowly. This is a question that I'm not sure we can definitively answer with the currently available observations, but it is a question that the next generation of Venus missions should answer and give us some exciting new information about. So I live in Tempe, Arizona, and in Tempe, there's a network of free buses that are all named after planets. And the bus that goes from my house to my office is coincidentally named Venus Forward. And so I think that's a coincidence, but it might not be given my research interests. And so a few months ago, I was very pleased that the higher ups at NASA decided to obey my bus and select a couple $2 billion worth of new Venus missions. So the newly selected Discovery missions, Da Vinci and Veritas, are going to revolutionize and essentially rediscover the second planet in our solar system. The timing of the selections was a bit inconvenient for me. I'm on the Venus panel of the Decadal Survey, and I was in charge of writing a large report that had to be turned into the steering committee the week that it turned out the selections were announced. So we had the report almost done. Then NASA made this amazing announcement for the Venus community, and I had to frantically revise the report. And then hours before the report was due, the Europeans decided to get on the action and select the Envision mission. So a week before I had to turn this thing in, there were no missions going to Venus. We were all very sad and demanding more. And then suddenly we had an abundance of riches, 3 brand new missions, 2 geophysical orbiters, and 1 deep atmospheric probe that will provide us the answers to some of our most eagerly awaited questions. And so I think the reason that the Venus community was so successful in capturing these mission selections is that there's a really compelling story to tell about Venus. And that story starts billions of years ago with the idea that our solar system might have had 2 habitable worlds. So it's possible that if you went back in time, you would find not 1, but 2 places in the solar system that had oceans, continents, a nice atmosphere, a nice surface, and possibly life. Recent climate modeling has shown that Venus, if it started habitable, could have remained habitable because of long-lived clouds until very recently in the solar system's history. Eventually, the sun brightened and the radiative forcing overwhelmed the Venus climate system, and so it would have entered a runaway greenhouse state and become the hellish wasteland that we see today. But it's possible that Venus and Earth, their surface conditions only diverged recently. So Venus could have had life and Earth-like conditions until quite recently. And in the maximalist version of this story, there could be life in Venus today? This is very speculative, but as Venus had a climate catastrophe, it's possible that some microorganisms could have evolved from the oceans to the last remaining niche in the planet that is habitable, which is the region of the clouds where the temperatures and pressures are still Earth-like. Earlier this year, there was an extremely high-profile paper published announcing the detection of phosphine gas, which is a biosignature on Earth and not thought to have an obvious abiotic process. And there's a lot of technical issues and maybe larger issues with this claim detection and its uncertainty, but it certainly did ignite some interest in the astrobiological potential of Venus. So the NASA administrator at the time tweeted that it is past time for NASA to return to Venus, a tweet that proved to be prophecy. And regardless of what you think about astrobiology and Venus or the phosphine gas detection in particular, the really striking thing about Venus is that we are so ignorant about its geologic history, and we are so ignorant about the abiotic processes in the atmosphere that we cannot immediately exclude claims that life exists today. Okay, so we know so little about Venus that there could be life abundant in the clouds that we simply haven't found yet. And so Venus is fascinating to study as an individual world. Again, even if you don't think there's life, there's a lot to love. This is my favorite image of Venus. On the left, we have Venus in the UV, and on right, we see the hot surface of Venus shining evilly through the clouds in the infrared. And so even if there's no life in the atmosphere is a fascinating place to study, and the surface and the interior are fascinated as well. And it's imperative that we understand Venus, not just as an individual world, but as one example of how rocky planets can evolve. Astronomers are detecting tens and soon hundreds of Earth-sized or Venus-sized planets orbiting distant stars. And because of the ways that we detect exoplanets, specifically the radial velocity and transit method, we are biased towards detecting exoplanets that orbit relatively close to their parent stars. And if you think that the planet-star distance determines whether or not a rocky planet will resemble Earth or Venus for most of its history, if that's true, that means that we are biased towards discovering Venus-like exoplanets. And we cannot claim to understand any rocky exoplanet if we don't understand Earth and its nearest rocky neighbor, which is Venus. So there's a very powerful motivation for exploring Venus. It's the missing link in our understanding of rocky planet evolution, with application to both our solar system and exoplanets. So if you weren't a Venus convert before and excited about the Venus missions, I hope you are now. My goal, I love Venus as a planet. I love almost every question about it, but my expertise is centered on the dynamics of planetary interiors. So we know that the rocky planets in our solar system are differentiated into metallic cores and silicate mantles, and it's vital to understand how those mantles and cores behave over time. And it's difficult to study because it's hard to directly probe the interior of a planet, and also the core is made of metal, and the mantle is made of silicates, but those metals and silicates behave very differently than metals and silicates on the surface of a planet, because any material, if you place it under extreme pressure and temperature, its behaviors will change quite a bit. So in general, I'm really interested in planetary interiors and their material properties and their dynamics. And today I'm excited to talk about how the interior of Venus and its evolution influence the surface. So let's talk about what we know about Earth and Venus. So we know, and I always say that Earth and Venus are similar in every respect, except the ways that actually matter. So just based on the basic statistics of Venus and Earth, you would think these two planets are identical. They're about the same size. They orbit at similar distances from their parent star, and they have similar densities, meaning they're probably made out of the same stuff. And if we were looking at two exoplanets with these properties, with our current technology, the current types of telescopes and instruments that we have, we would be unable to distinguish a Venus analog exoplanet and an Earth analog exoplanet in any way. If you were an alien looking back on our solar system, with the technology that we humans have today, you would think that Venus and Earth are the same planet because they're so similar in terms of their bulk properties. Okay, so we do know that Earth and Venus are dissimilar in several important respects. The surface of Venus is hot enough to melt lead. It's not a nice place to visit. But what we know about Venus, and in particular its interior, is quite limited. And it's so limited that I can actually run through the main insights we've gained from the history of space exploration at Venus so far. So the Soviets have sent multiple landers to Venus, and they've made some geochemical measurements of the rock compositions. And from petrological analyses, we can infer that the mantle of Venus is about as hot as the mantle of Earth and could possibly be 100 or a few hundred degrees hotter. The Pioneer Venus orbiter placed the best available constraints on the magnetic and plasma environment of Venus, and it failed to detect any intrinsic magnetism of Venus. So we know that Venus does not have an Earth-like core dynamo that produces a global magnetosphere. As far as we can tell, Venus has no intrinsic magnetic field, but as I'll get back to at the end of the talk, the upper limit on the magnetism of Venus is actually quite permissive. Now, the Magellan mission, which is the one that entered orbit around Venus 10 days after I was born, it made the best available maps that we have of the surface in radar wavelengths. And I could say quite a lot, and I'm sure many of you in the audience could say even more about the spectacular science that came back from Magellan. But the big picture takeaway is that Venus does not have an Earth-like system of plate tectonics. There's no obvious mid-ocean ridge analogs. We don't think that the lithosphere or the crust of Venus is broken into easily identifiable plates that behave in the way that plates behave on Earth. And finally, the most recent major advance in understanding the interior of Venus is that the moment of inertia was quantified for the first time in a paper earlier this year. Unfortunately, the moment of inertia was only quantified to about the 10% level. So we can now say definitively that Venus probably does have a metallic core, but we can't say much about how big the core is or whether or not the core is solid or liquid. So we know that Venus has a hot mantle. There's no magnetic field. There's no plate tectonics. So I think more than knowledge, what the summary of the current exploration of Venus reflects is the uncertainties that we have about Venus's interior and its evolution over time. So what I want to talk about, the reason I'm so focused on Venus's interior is that Venus, like all planets, is a heat engine. It is an engine that converts its internal heat into interesting phenomena. So many of you might care about things that are relevant to surface dwellers, like the composition of the atmosphere, how big the atmosphere is. You want to know how much volcanism or tectonics is occurring on the surface. You want to understand if a magnetic field mediates atmospheric escape processes over time. And if you want to understand any of those sort of surfacey things, you need to understand the interior, because it is the motion of the mantle, the turning of the core that gives you these phenomena over time. And so before asking a question about Venus, I just wanted to briefly summarize Earth's energy budget as a starting point for comparing Earth and Venus. So the fundamental observation for Earth is that the interior of Earth is losing heat to space. And the total heat flow, if you add up all the heat flow that's coming out of Earth's interior, it adds up to about 46 terawatts. The number is not that important. What is important is that heat budget is roughly partitioned into two roughly equal sources. So the first way that Earth loses heat is by cooling down. The temperature of Earth is dropping over time. The second reason that Earth has heat to lose is that heat is being produced in the interior by the ongoing decay of radioactive isotopes of elements like potassium, uranium, and thorium. And it turns out that these two sources of heat in the interior are almost equal today for Earth. And we think that the secular cooling, or the temperature decrease of Earth, is about 2/3 of the heat associated with that comes from the mantle, and about 1/3 of the heat of that comes from the core. Now the mantle is about 2/3 the size of the core, so it works out to the mantle and the core cooling at roughly the same, at similar rates over time. In contrast, the radiogenic heat budget of Earth about half of the radioactive isotopes are sequestered in the crust, and the rest of them are in the mantle. So this is Earth's heat budget. And now you can start thinking about how Earth and Venus might be different. If you think that Earth and Venus are made out of the same stuff, maybe they have abundant, similar amounts of radiogenic heating, but because Venus doesn't have plate tectonics, its mantle dynamics are completely different. And so you might expect the secular cooling rate to be quite different between Earth or Venus. So that's the question, basically. Is the total heat flow out of Venus similar or less than the total heat flow out of Earth? If the heat engine of Venus is running quickly, you might expect it to have an Earth-like value, or you might expect that the heat engine of Venus is running slowly, meaning that this total heat flow would be less for Venus than for Earth. And so even without plate tectonics, Venus must have mantle convection. Venus's mantle is hot because of the gravitational energy of accretion and because of radiogenic heating. And so if you calculate like a Rayleigh number for the mantle, it must be convecting. And that means that there should be stuff moving up in the mantle, there should be stuff moving down in the mantle, and to accommodate that vertical motion, you must have horizontal circulation, especially at the top of the mantle. So you should have volcanic outgassing from the partial melting of the mantle. You should have both compressional and extensional tectonics of some form. And the atmosphere is, of course, interacting with the space environment. So you can have various types of atmospheric escape that are removing material from the Venus atmosphere. And the atmosphere also could be losing material to the surface via various weathering processes. And so if the core of Venus is hotter than the core, than the bottom of the mantle, you expect there to be heat transfer from the core to the mantle, and that's currently insufficient to give us a magnetic field, but it's a question how much faster you need to cool the core to get a magnetic field on Venus. Okay, so Venus is a heat engine. There must be mantle convection that must produce some amount of tectonics and volcanism, but it's unclear what the rates are relative to Earth. And so before actually trying to present evidence about how fast this heat engine is running, I wanted to take a survey of all of you to see what you think, what your pre-existing guess is, or what you've gleaned so far from the introduction. So we're going to do some democracy. To prove that you're listening, I want everyone to go to the reactions, which they should, I believe, be able to see in the participants window or something. And if you could click, I want you to answer this question if you can. So do you think that Venus is cooling slowly relative to Earth, meaning that its heat engine is running slowly relative to Earth? And the way I want you to indicate your vote on this is to use the reaction. So if you could select yes if you think that Venus is cooling slowly relative to Earth, and select no if you think that Venus is cooling as fast as Earth is, or possibly even faster. And the votes are trickling in. They're tied so far, but only 4 people have voted. So you still have a chance to change the results by registering your opinion. And even if you're not sure, please feel free to take your best guess. Okay, and if you can't find the reactions, maybe it's a bit buried, feel free to just type your answer in the chat, either a yes or no. I think the chat window is a bit more accessible. All right, I'll give some time for the results to come in, but it seems like people are evenly divided, which is good because I am too. So what I want to do today is not necessarily to give you a definitive answer to this question, but to make the case for both sides. So I'll start the seminar by making the case for slow cooling of Venus relative to Earth, and then I'll give some countervailing evidence to suggest that Venus actually might be cooling as fast as Earth is. And I'll conclude by explaining some observational tests of the cooling rate of Venus, which will be achievable with the next generation of Venus missions, but which will also motivate sending even more missions to Venus in the future to gather some crucial data that Veritas and Vision and Da Vinci won't be able to collect. Okay, so we'll start with the case for slow cooling, which might be the case that people are more familiar with because the slow cooling hypothesis has really been the reigning view since Magellan, I would say. So the first observation is something I've said already. This is colorized topography from the Magellan mission. Venus doesn't have plate tectonics. What it has is a bit of a mystery, but we know it doesn't have an Earth-like system of subducting plates and mid-ocean ridges. And there's also the suggestion that not only does Venus not have plate tectonics, from the cratering record, people have hypothesized that Venus doesn't have much activity of any kind today. So you might be familiar with this old story. There's only 1,000 impact craters on Venus, and their latitude and longitude coordinates are consistent with a random distribution. And if you look at the actual images of the craters on Venus, only about 10% of them look like the crater over here on the right, a crater which has been very obviously embayed by volcanic flows that buried the rim of this crater and filled up most of the interior depression of the crater. And so one way to get this unique cratering record on the surface is to invoke an episode of catastrophic resurfacing about 1 billion years ago, which wiped the surface of Venus clean. Now, if you assume that crater-producing impacts happen about once every 1,000,000 years, if you don't have any more volcanic activity or only have a little bit of volcanic activity, then after 1 billion years, you've built up this record of 1,000 craters. And studies indicate that the location where where impactors actually hit Venus is mostly random. And so if you don't resurface anything after this catastrophic event, you get a random distribution of craters on Venus. So this was a model paper by Strom et al. Soon after the Magellan mission that has held sway over a lot of the community since. Okay, and so the question is, if Venus doesn't have plate tectonics, what is the alternative mode of mantle convection? And the reason that plate tectonics cools the interior of a planet so efficiently is that when you have plate tectonics, you are recycling the entire lithosphere into the mantle. So you're carrying that cold stuff down into the mantle where it can warm up and basically steal heat from the hot mantle. You could put that lithosphere, if it goes all the way through the mantle, you can put it next to the core and suck a whole lot of heat out of the core. But also when you have a divergent plate boundary, you're opening up a gap for hot material from the mantle to rise up to the surface where it can cool directly to space. So in plate tectonics, the entire boundary layer of the convective system participates in convection, and that lets you remove heat from the deep interior very efficiently. So one alternative to plate tectonics is this stagnant lid mode of mantle convection. In the stagnant lid, the lithosphere is not broken into plates. It is instead a stagnant planet-wide lid that basically acts as a thermal cap on the entire planet. So in the stagnant lid mode of mantle convection, in a simple cartoon form, there is a boundary layer at the top that does not participate in convection. And there's a thermal insulator. So in order for heat to be lost, it has to be conducted through that stagnant lid, and that's slow. And so models show roughly that if you have stagnant lid convection on a planet, that will reduce the total heat flow by about half relative to if you had plate tectonics. So a stagnant lid is a significant impediment to the running of a planetary heat engine. And so we think that Mars today is like the classic example of a stagnant lid planet. And you could put other sort of boring worlds like the moon on the Mars end of the mantle convection diagram. Sorry, no offense to people if I call Mars or the moon boring. I like them too. I have students working on both planets. But you could make a sort of, a view of mantle convection might involve like an n-member diagram like what you have on this slide. You have mobile lid plate tectonics at one vertex. You have crazy heat pipe volcanism, where the predominant mode of heat transfer is actually just advection of hot magma. That could be another point of this triangle. And then you could have stagnant lid convection, where the primary mode of heat transfer is conduction through a thick lid on another vertex of this triangle. And so in the canonical view of the evolution of Venus, you would place Venus basically right on top of Mars at present day, and say it's on the Mars-like end of the Earth and Mars end members of how mantle convection works. Okay, and then so we can ask ourselves how this all relates to the lack of a magnetic field. So before talking about why Venus doesn't have a magnetic field, I should say a few words just to level set so we all have a shared understanding of of why Earth has a magnetic field. So Earth has a super strong dynamo that's produced a strong global magnetic field that's survived for at least 3.5 billion years and possibly 4 billion years or more. And if you ask the Insane Clown Posse, they won't be able to tell you why Earth has a magnetic field. But scientists can tell you that Earth has a magnetic field because the outer core of Earth is a liquid metal with about the viscosity of water. It's churning vigorously, and that produces a dynamo via magnetic induction. So the reason Earth has a magnetic field is that it has a vigorous convection in the core. So the reason Venus does not have a magnetic field is that Venus lacks vigorous convection in the core. The core could be hot, it could be liquid, but it can't be convecting. And so this is sort of a natural prediction of the stagnant lid models of Venus. So if you have the mantle cooling slowly, well, the mantle insulates the core. So if the mantle isn't losing heat to the surface, the core is not going to lose much heat to the mantle. And so Francis Nimmo did some pioneering work on this. And in his models, back in 2002, he published a thermal evolution model where you have a transition from plate tectonics to stagnant lid convection about 1 billion years ago. And what happens when that transition occurs is that the mantle actually starts heating up because the radioactive heat production is greater than the heat flow from the mantle to the surface. And as the mantle heats up, the thermal contrast between the core and the mantle starts to disappear, and the core heat flow drops to 0. So it makes sense that you don't have a dynamo. The core isn't cooling down, it can't convect, and so there's no dynamo. Okay, so that's basically in broad strokes the case for slow cooling. And I would say that this is the popular hypothesis, and it's maybe the one I come down on now. I don't know though, and the reason I don't know is because there's been a lot of work in recent years to suggest that the interior of Venus is actually cooling much more quickly than we previously believed. So I want to run through some reasons why this slow cooling model might be completely wrong. Okay, so first is the observation that Venus does not have plate tectonics, but it also doesn't have a stagnant lid. So again, in the stagnant lid picture, the entire lithosphere is fused together. There's no like vertical motion of the crust like near the surface, or very, very limited. It's not broken into places, into pieces. However, there is evidence that subduction is occurring at least locally on Venus. So there's this great paper in Nature Geoscience back in 2017 that argued that mantle plumes had caused local subduction and are currently causing local subduction at the Artemis and Quetzalcoatl coronae. This is a picture of Artemis, the largest geologic feature on Venus, here on the left. And based on gravity and topography data and geologic analyses of radar images, what we think is going on here is that there could have been a mantle plume that rose up and actually broke the lithosphere under Artemis coronae. And then the plume material could have intruded to the surface or extruded on the surface and weighed down the lithosphere. And in fact, weighed it down so much that the lithosphere broke, and subduction is occurring today. So the subduction zone on this image would be basically down here in the bottom right, where there are all these concentric fractures. And just outside of the concentric fractures, there's a topographic low that looks quite a lot like a trench that you would find at a convergent plate boundary on Earth. And the gravity data support the idea that subduction could be here, occurring here as well. Okay, and so the plume-induced subduction, just last year, a great paper led by Anna Gulcher made numerical models that showed how this process could be occurring. And this paper was really impactful because they looked at the morphology of basically all the coronae on Venus, and they found that at least 20% of the coronae on Venus, especially the larger ones, had morphology that indicated that they could be still active today, meaning that there's mantle lithosphere interaction that is ongoing today and potentially leading to localized subduction and delamination and volcanism and tectonics more generally all over the planet. And this was a really exciting result. But ideally, we would like to, if we want to constrain the total heat flow out of Venus, we would like to directly measure the heat flow. Now, the best way to do that would be with some sort of probe, but as InSight has shown, it's actually really hard to directly measure the heat flow. So perhaps the best way we have of getting an actual number for the heat flow today is to infer the heat flow locally at certain geologic features by looking at lithospheric flexure. So the general idea is that for flexural studies, it's a sort of basic geophysical technique, is that if you have a load on the lithosphere, like a volcano, here a pancake dome is illustrated, if you have a load on the lithosphere, it's going to bend the lithosphere down. And the wavelength at which the lithosphere bends down and has this forebulge and then flattens out again is dependent on the thickness of a lithosphere. If you just assume that the entire lithosphere is purely elastic, you get the elastic thickness of the lithosphere. Reality is a bit more complicated because brittle failure occurs at the top of a lithosphere, and ductile flow will start to occur at the bottom of a lithosphere. And so really the real mechanical lithosphere is thicker than the idealized elastic lithosphere. But if you have a yield strength envelope for the crust of Venus, you can associate the base of the mechanical lithosphere with a certain temperature. And so if you know the mechanical thickness of a lithosphere and you know the temperature at the base of the mechanical lithosphere, you can calculate the temperature gradient between the base of a lithosphere and the surface. And the heat flow through the lithosphere is directly proportional to this temperature gradient. It equals the thermal conductivity of a lithosphere multiplied by the temperature gradient. So if you know this temperature gradient, you know the heat flow. And so you can use volcanoes or volcanic features as a local probe of the heat flow on Venus. And so these flexural studies I've been involved with for the past several years, and I have a wonderful PhD student, Madison Borelli, has been working with me on this and just published some exciting results. So the overall picture is that there's different types of volcano-tectonic features on Venus. And Pat McGovern, back in 2013, and in a series of papers, hypothesized that many features that resemble coronae should be found at locations with pretty low elastic thickness, whereas large conical volcanoes should be found at regions with really high elastic thickness. And that's because the elastic thickness controls whether magma can ascend vertically or whether it'll spread out horizontally as it goes through the lithosphere. And then we hypothesized that the elastic thickness might be sort of intermediate at other volcanic features on Venus, such as these pancake domes. So over the past few years, me working with Sue Smrikar and with Madison have searched for flexural signatures around coronae and steep-sided domes. Pat actually back in 2013 found, and we conducted a similarly fruitless search, that the volcanoes, these large conical volcanoes, have basically filled in their own flexural moats with lava, and so you can't see the topographic signature of flexure around these conical volcanoes. Okay, but using Magellan data, we were able to search for lithospheric flexure around coronae and pancake domes. So I'll walk you through how we did that search and what we found. So first of all, here is a map of a coronae on 20% of Venus. I wouldn't pay too much attention to the difference between the type 1 and the type 2 coronae, which are represented by the circles and diamonds here. What you want to focus on is the difference between the empty symbols and the filled symbols. The filled symbols are where we were able to find topography that was amenable to a flexural interpretation using the Magellan data. The difficulty of doing this study is that the Magellan topography is not a super high quality data set by modern standards. So the global topography has a spatial footprint of like 10 kilometers or worse. And so it's hard to resolve these features. Fortunately, for about 20% of the surface of Venus, back in 2012, Robbie Herrick made available stereo-derived topography from regions of the surface where there's overlapping coverage in stereo radar images. So that topographic data set is much better for trying to find these flexural features. But despite the low resolution of the available topography, we were able to find flexural signatures around quite a lot of coronae. And Madison recently conducted a global survey of pancake domes, because there's only 100 pancake domes on the surface of Venus. And she was also able to find flexural signatures around about 20% of the pancake domes. I should note that Veritas and Envision are going to collect much better topography for the entire planet. And so people will be able to blow our studies out of the water. You should be able to find these sorts of flexural signatures that I'll show around hundreds or thousands of features on Venus, not just the tens that I'll report today. Okay, but the general workflow to look for flexure around a geologic feature is to extract radial profiles of elevation from the topography data. So you start out the feature. Here there's a pancake dome that's actually too small to see in this image. And you take several hundred kilometers worth of radial topography. Now, in this particular case, the profiles are plotted here in the center, and you select the ones that are amenable to a flexural interpretation. So this red profile, you can see the trench, you can see a forebulge, sort of, and you can see the topography flatten out. And, but the other profiles sort of look like nonsense, which isn't surprising if you look at the image. This is the one profile that doesn't obviously cross some other like volcanic or tectonic structures. So this is a particularly bad example, but there are features on Venus where you can find multiple profiles that have these flexural signatures. Anyways, for any profile that has a flexural signature, you can fit plate bending models to them in order to derive the elastic thickness. And then using the yield strength envelope for the crust, you can get a mechanical thickness for the lithosphere and then a heat flow. So that's the overall workflow. We tested a bunch of different types of plate bending models and also a few different assumed rheologies to get the mechanical thickness. And what we found for coronae is that the elastic thicknesses were almost exactly what was predicted. They're all like in the 5 to 10 kilometer range. And if you translate that into a heat flow, you get heat flows around 100 milliwatts per meter squared. What that works out to is about the average heat flow on Earth. So if you assume that these heat flows we inferred around coronae are globally representative for Venus, you would conclude that the Venus heat flow is actually Earth-like. It's not the sort of half Earth-like values you would expect for a stagnant lit Venus. Okay, well, maybe an obvious objection to that is that, well, maybe the coronae heat flow is just representative of the heat flow at coronae and not globally. And the counter to that is that, well, not actually a counter, something that actually supports that is that around pancake domes, the inferred elastic thicknesses are quite a bit higher. They're like 30 kilometers plus or minus 10. And those work out to more Venus-like, in terms of the model predictions, Venus-like heat flows, except the pancake domes that are near coronae are associated with coronae-like heat flows. So just to give an example a bit more of how this all fits together, let's consider Aramati corona, which is a very, very nice looking corona here. It actually has a pancake dome called Nerina Tholis, which is here on the left. And we found back in 2018 that the elastic thickness at Aramati was inferred to be about 13 kilometers, corresponding to this like 100 milliwatt per square meter heat flow. So us and also Meg Russell and Catherine Johnson found that the elastic thickness inferred near Nerina Tholi is much smaller, like 2 or 3 or 4 kilometers, which equates to pretty high heat flows. And this actually matches models by Anna Gulcher and colleagues that predict the peak heat flows of 100 to 200 milliwatts per square meter during the formation of this particular corona. This is one of the examples in their modeling paper. So far, the observations, the data analysis, and the modeling are fitting together. Coronae especially are associated with mantle lithosphere interactions that involve at least transient heat periods of high heat flow, which is what you would expect to be reflected in the flexural data. However, by comparing these localized estimates to global gravity and admittance data, you could get a better understanding of whether or not the heat flow is not only high at Coronae, but high globally. And Sue Smrekar is leading, and I am assisting with a magnum opus on that topic, and I'm not allowed to share its conclusions with you now, but stay tuned, and there could be a sort of a capstone to this line of argument in the pre-Veritas, pre-Envision era. Okay, so if Venus doesn't have a stagnant lid, and I think that's like pretty conclusive at this point, if there's at least localized subduction and delamination occurring, what is the reigning mode of mantle convection? So recently there's this idea of a Plutonic squishy lid, which is a new mode of mantle convection that's sort of in between the other end members of mantle convection. Now, the Plutonic squishy lid occurs when you have a very high fraction of intrusive magnetism relative to extrusive magnetism. And if you intrude a lot of hot magma into your lithosphere, what happens is that the lithosphere becomes warm and thin. Now, the global heat flow is inversely proportional to the lithospheric thickness. So a thin lithosphere necessarily leads to a high heat flow. The counterintuitive thing about the Plutonic squishy lid is that because the magmatism is intrusive, the lithosphere is thin, and you can lose a lot of heat. The mantle can lose a lot of heat by conduction. And that means that relatively less heat is transported by magma. So the relative fraction of intrusive magmatism is high, but the relative fraction of heat transported by magmatism is less in this Plutonic squishy lid regime. So this is the cartoon Plutonic squishy lid on the left, and we can place it on our, sorry, I'll come back to this, on our little ternary diagram here. So previously we thought that Venus was on top of Mars on this ternary diagram of mantle convection regimes, but maybe the Plutonic squishy lid means it's somewhere in the middle. There's heat that's transported locally by subduction or delamination. There's quite a lot of heat flow by conduction because the lithosphere is thin, thinner than you'd expect for a stagnant lid. And there's some heat that's being transported by magmatism. So Venus is not an end member of mantle dynamics. It is a unique cocktail of different modes of mantle convection that rewards careful study. Okay, moving on. So if Venus is actually cooling quickly, that poses a problem. It becomes more difficult to explain why Venus lacks a magnetic field. In the canonical story, it's easy to explain the lack of a magnetic field because the core is cooling slowly. But if the core is cooling at the same rate for Venus and Earth, then you have a difficulty. You have to then say that there's something different about the core of Venus that means that even if you cool it at the same rate as the core of Earth, it won't produce a dynamo. And the way to do that is by invoking chemical stratification in the core of Venus. This is sort of a complicated story. I'm going to run through it real quick just because I have some other things to say. But if you don't understand it, feel free to ask me later. So this is an idea that was popularized by Seth Jacobson and colleagues back in 2017. And the idea is that if you think of how Venus was built, it started as a small protoplanet and it grew over time as more material was added. Now, the material that was added late to Venus contained both metal and silicates, and the metal that later went into the core would have equilibrated with the silicates at hotter temperatures and higher pressures, because as Venus grows, the internal temperatures and pressures both increase. And it turns out that if you equilibrate metal and silicates at more extreme conditions, more light elements like silicon and oxygen go into the metal. So the metal that you're adding last to the core of Venus will be relatively rich in silicon and oxygen. And so if you just build the core of Venus in this nice regular onion shell sort of way, the outer layers of the core are really low density compared to the inner layers. And this density gradient is incredibly stable against convection. You need to cool the core down by thousands of degrees in order to get it to convect, which is simply implausible. And so the core of Venus would never convect. And the idea is that the reason that Earth's core avoided this stagnant fate is that we had a giant moon-forming impact right at the end of accretion that totally like mechanically mixed up the core, stirred everything together, so the core started chemically homogeneous. But if Venus never had a giant impact, or if the giant impact occurred relatively early in accretion and not at the and wasn't like the last thing that happened during accretion, Venus might have this weird chemical structure that would mean that the core never convected. So that's the explanation for why you have no dynamo in the absence of plate tectonics. And before anyone asks, even though Venus is rotating slowly, we think that it's still rotating fast enough that it should have a dynamo if the core is convecting. So I don't think you can blame just rotation for the lack of a dynamo. I have to say that, otherwise someone will ask me about it. So forgive the rant. Okay, so that's the case for and against slow cooling. So the case for slow cooling is just the canonical picture of what happens if you don't have plate tectonics and don't have magnetic field. But these flexural estimates of the actual heat flow seem to suggest that in a lot of places, Venus is losing heat quickly, or at least did at some point. New models of mantle dynamics show that Venus does not have a stagnant lid, and there are modes other than plate tectonics that can cool the planetary interior efficiently. And finally, some new ideas about core formation may mean that whether or not you have a magnetic field might not be the best proxy for the cooling rate of the core. Okay, so let's talk about how to test these ideas. Obviously, the best way to test it would be to get much better direct measurements of the heat flow, either by doing these flexural studies at much higher resolution, at a much greater number of features, with gravity data that can actually resolve these geologic features, or with a probe. That would be the best way to answer this question. But in the absence of that, there's several other tests we can undertake by ameliorating other aspects of our ignorance about Venus. So the first hypothesis that I'll throw out there is that if Venus has been cooling slowly relative to Earth, the mantle of Venus should not be fully solid. So the idea here is that if there's slow cooling, the mantle is hotter than Earth's mantle at present day and has stayed hot over time, meaning that if it started cooling, solidifying, from the middle out, there could still be this basal magma ocean of liquid silicates that could be hundreds of kilometers thick. My slides have run away from me. They've gained sentience, and they know that I need to be stopping for conclusions in a few minutes. But don't worry, slides, I'll get there. And so in this picture, the core of Venus is hot and fully liquid, but it's stagnant because it's not cooling down. Okay, so just very briefly, what is a basal magma ocean and why would it still exist on Venus? So the idea is that the bridgemanite crystals that form the bulk of the mantle are neutrally buoyant at about mid-mantle depths, pressures of 50 gigapascals. So it's possible that unlike Mars or the moon, if you have a magma ocean on Earth or Venus, that magma ocean will solidify not from the bottom up, but from the middle outwards. The superficial magma ocean solidifies really quickly because it can radiate heat directly to the cold, heartless void of space. So depending on whether or not you have a thick atmosphere, that might take 100 million years to solidify, but that's still a geologic eye blink. In contrast, this basal magma ocean is very insulated. The solid mantle acts as a big thermal blanket. And because the basal magma ocean and the core are both low viscosity fluids, there can't be a significant temperature contrast between them. So if you want to cool down the basal magma ocean by 1 degree to freeze it a little bit, you have to cool the entire core down by 1 degree as well. So the core acts as a big thermal insulator, and the solid mantle acts as a big thermal blanket. So there was a famous Nature paper back in 2007 led by Stéphane Labrosse, and they published models that showed that Earth could have had a basal magma for about 2 billion years. Well, if you cut down the cooling rate of Venus by a factor of 2 relative to Earth, the lifetime of the basal magma ocean doubles. So a basal magma ocean that would have solidified 2 billion years ago in Earth would still survive today in Venus. And so Venus has the internal structure of like middle-aged Earth because the internal temperature of Venus sets its structure. But the dynamics of Venus are different than the dynamics of middle-aged Earth because it's the rate of change of temperature that determines the dynamics. So if you want to see all the detailed simulations with all the math, you can check out my 2020 paper in GRL. Okay, and another fun fact about the basal magma ocean is that it could be a reservoir of noble gases. I'm just going to sort of chum the waters here, and a student working with me has a great presentation at AGU this year about it. But the idea is that Venus has less radiogenic argon in its atmosphere than Earth does. We don't know about like the xenon, a radiogenic xenon, and the helium story is complicated. And recent mineral physics experiments show that argon-40, like potassium, is incompatible in the deep mantle, meaning that as the mantle solidifies, whatever noble gas or potassium started in the basal magma ocean would stay in the basal magma ocean until the basal magma ocean solidified. And even then it would take maybe 1 billion years or so to get mixed in the whole mantle and degassed to the surface. So the basal magma ocean could be this hidden reservoir of noble gases. Another point I want to make is that if the slow cooling hypothesis is correct, it's quite possible that Venus had a dynamo in the past, and therefore we could detect crustal remnant magnetism. Something that people have realized only in the past few years is that the silicates that comprise or that make up this basal magma ocean are electrically conductive if they're under extreme pressures and at extreme temperatures. So it's not only convection in the core that can give you a magnetic field and a dynamo. Convection in the basal magma ocean can also produce a dynamo, even though the basal magma ocean is made of silicates. To make a long story short, in any model where Venus starts with an Earth-like core, it's easier to generate a dynamo in the past than it is today because Venus was cooling down faster in the past than it is today. So here's some models with Cedric and Paul Tackley that show that we predict that Venus truly doesn't have a dynamo today, but it had one for billions of years in the past. And if you add the basal magma ocean to this, you also predict that there was a magnetic field for the past couple billion years. And the big point I want to make is that the crust of Venus can preserve a signature of an ancient dynamo. So just like on Earth, if you have a volcano on Venus, it'll erupt, it'll have magnetic minerals like magnetite, and the surface temperature of Venus is about 100 degrees below the Curie point of magnetite. So as the igneous rocks on Venus cool, they're going to lock in the direction of any ambient field. If there's no ambient field, the directions will just be random. But if there was a dynamo in the past, the volcanic rocks could lock in that signature of the magnetic field. And even if you're 100 degrees below the Curie point, that's still far enough away from the Curie point that that magnetic remnants is stable for billions of years. You have to get within a couple tens of degrees of the Curie point for the magnetic remnants to viscously decay in geologic time. And so if you just do some simple calculations, and these are all discussed in a 2019 paper I had, you can conclude that the depth of crust that could be magnetized on Venus could be a few kilometers, like 5 kilometers. And that's just the surface temperature divided by the blocking temperature minus the surface temperature divided by the sort of thermal gradient that you get from these heat flow studies. And so you have to go down about 5 kilometers in the crust of Venus before things get hot enough that all your magnetism is erased. And the other point I want to make is that we have this this constraint, this upper limit on the dipole moment of Venus from Pioneer Venus Orbiter. And in actual like magnetic units, it's like almost 10 to the 18 amperes meter squared. Those are weird units, but I want to emphasize that this 10 to the 18 is like a big number. So the way you get that number is if you take a typical magnetization intensity, which is conveniently like 1 ampere per meter, and you consider a depth of a few kilometers for magnetization, this 10 to the 18 number up here is consistent with 33% of the surface of Venus having crustal remnant magnetism. So I think it's quite possible that if we conduct a magnetometer survey at low altitudes, we would find some crustal remnant magnetism. There could be a lot that awaits discovery. Okay, so I'd ask you, maybe this will get buried under questions, but I want you to think about if your answer to this question has changed or if I've just confused you. But just to summarize, there's basically, well, actually, maybe what I'll say is just that thanks NASA, thanks ESA for sending us Venus missions. We're going to learn a lot about the surface geology, the surface geophysics, the noble gases, and the interior structure of Venus from this new fleet of spacecraft that are going to the second planet. But there are all sorts of geophysical investigations that these missions will not conduct. In particular, they're not going to look for coastal remnant magnetism, and they're not going to directly search for seismic activity on Venus. And because Da Vinci is just a probe that's going through the atmosphere at one location at one time, it's really good for measuring the abundances of things that you expect to be well mixed in the atmosphere, like noble gases and other isotopes. But to understand the Venus atmosphere as a system, to understand all the cool photochemistry that goes on in the clouds, to assess the habitability of the clouds, we really need atmospheric measurements and meteorological measurements at a lot of different local times and locations and long baseline monitoring. So despite the fact that Venus has had a lot of success recently, there is no need to stop selecting Venus missions, just like we didn't stop selecting Mars missions after the Mars exploration rovers or something. And I think a logical next mission for Venus would be an aerial platform that can do these cool geophysical investigations and also make really interesting atmospheric measurements. So with that, I'll sort of leave up this, this table that summarizes the evidence for and against a rapidly running heat engine on Venus. And I'm eager to hear your questions and what you think about all of this. So sorry for running a little long, but I hopefully left a little bit of time for questions.
Thanks so much, Joe. That was a really great talk. I know it's sometimes a little bit hard to get a sense for the audience appreciation with these online settings. So if you enjoyed the talk, please make sure to let them know in the chat. So I see a couple questions already. Will we ever see a rover on Venus? And maybe it would have to go back to vacuum tubes.
Yeah. So there's all sorts of ideas about clockwork rovers. But first, I think we need to understand like the geologic units on Venus because for Mars, we can send rovers to places where we know that over like a couple kilometers, you can sample a lot of different units and you understand their larger context from orbit. I don't think we really know that on Venus right now. So right now it doesn't, like a lander would make a lot of sense. But I think Veritas and Envision will tell us if there's a perfect place to send a rover where we would really want mobility to do exciting science in the future.
Robert Baltos asks, I thought the rotation of Venus, which some consider retrograde, was explained by an impact. Is that not a popular model?
I would say that the popular thing is to be confused about the rotation of Venus, or at least that's my thing. So yeah, you can evoke an impact to tip it over, slow it down. But also because Venus has such a thick atmosphere that is super rotating today, there could be a lot of angular momentum exchange between the atmosphere and the solid body over time. And so it's not clear to me what we would expect the rotation rate of Venus to be if it didn't have an impact, given this complicated atmospheric story. And so I think we need new data, new models to answer that.
Great.
Sorry, Cedric, yes. Cedric probably knows way more about this than I do, so ask him.
Stanley asks, is the supervolcano model still alive? I presume that's referring to the complete overturn of the crust.
The catastrophic resurfacing model, I don't think it's dead yet. I think that Veritas and Envision will definitively test it. I mentioned that only 10% of the craters on Venus are like obviously embayed, but there's controversy about whether or not like 80% of the craters are partially embayed in sort of a way that's not obvious in the Magellan mission. If they are, then catastrophic resurfacing is dead. If they're not, then some catastrophic resurfacing survives in some flavor. But this end number of like literally the entire like crust of Venus, like turning inside out all at once instantaneously, that's probably too much of a cartoon. And I know like Walter has some ideas about how you could get massive volcanism over like 100 million years or so as Venus underwent a transition to mantle dynamics. So that's when I say some flavor of catastrophic resurfacing, as opposed to just a purely like uniformitarian view of Venus evolution.
Kind of a admittedly totally left field question. Could we get rid of the CO2 atmosphere someday?
Yeah, so everyone should read a sci-fi book that recently came out by it's called The House of Sticks. It's about these Quebecois separatists who live in these floating cloud platforms, and and have various geopolitical goings-ons. And they find a wormhole, actually. Oh, sorry, spoilers. They find a wormhole in one of the chasmata on Venus that very efficiently sucks out the atmosphere to another galaxy, I believe. So I think that's probably the best way to do it. But if you have a more practical terraforming suggestion, I'm interested to hear it.
Christine Shupla asks, does this model for Venus's core and its implications for magnetism have any implications for Mercury's magnetic field and core?
Yeah, probably. I've never published anything about Mercury, but yeah, if you think that Mercury, the reason it has such a high core mass fraction is that it had its mantle stripped by an impact, then it's quite plausible to think that maybe the giant impact like helped homogenize the core and set the stage for dynamo. And if I could answer Julia's question, yeah, so these stories I think have a lot of implications for exoplanets. Hopefully in 20 years or so, we'll be able to detect the radio emissions from exoplanetary magnetic fields. To detect the magnetic fields of rocky planets like Earth or Venus, you probably need to go above Earth's atmosphere. You need like a radio telescope in space to get away from the ionospheric cutoff for Earth. And so if a dynamo is like a stochastic outcome of accretionary processes, you'd expect the existence of dynamos to be sort of uncorrelated with atmospheric properties or with planet-star distance. But if it's this long-term planetary evolution, mantle dynamics, which is really controlled by surface conditions, which is really controlled by planet-star distance, then you would expect like all the planets in the Venus zone close to the star to have no dynamos, or at least the old planets wouldn't have dynamos, whereas the planets that are further away from the star and might be more Earth-like, they would be more likely to have global magnetic fields. So actually, maybe we can test this in our solar system by searching for crustal remnant magnetism on Venus, but magnetism is so complex, and our solar system, like every rocky world in our solar system, is a special snowflake. We really need a huge data set enabled by exoplanets to gain a complete picture of planetary magnetism. Okay, rant over.
All right. It is 4 o'clock, so unless we have any burning questions, oh, but we do, and it just came on through from Pacific. People have also invoked pebble accretion as a way to accrete softly a cold planet that could have a stably stratified core. Not sure how that precisely works. More of a comment.
Yeah, I'm mad about pebble accretion because I TA'd a graduate planet formation class back in like 2013, 2014, and like everything I taught to people was like wrong. So it's, now we have this whole new theory of how planets are born that really is going to cause us to throw out a lot of our models. But that's good because it means we all have something to do.
All right. Well, thanks so much for coming, everyone. Pat McGovern mentioned some ongoing commentary on Twitter to check out regarding.
All right, I'll open that app with trepidation. Thanks, Pat.
So I really appreciate you coming. It was a great talk. The next LPA virtual seminar will be next week with Dr. Mark Panning from the JPL, who will be talking about planetary seismology. So please keep your eyes open for that announcement. And have a great day. Have a great afternoon, everyone. Thank you again.